Hi everyone, in this video we're going to be looking at the calculus of logarithmic functions. So we've done the derivatives of functions like e to the power of x, trig functions, all kinds of different functions, but now we're going to look at the derivatives related to logarithmic functions, and in particular the natural log function here. Okay, so the syllabus says, and we've already done the first couple of things where we've defined what the natural logarithm is, log base e of x. We've talked about the relationship and the inverse relationship in the last unit between e to the x and ln x. So what we're going to do is establish and use the formulas for the derivative of ln x in this video, and then in the next one we'll talk about the integration of ln x and derivatives and using the chain rule for logarithmic functions. So let's start the derivation of this result by looking at one that we do know, which is the y equals e to the x. We know that the derivative of y equals e to the x is e to the power of x. So let's start from there, and we're going to use that. I'm going to start with the function that we're looking at here, y equals ln x, that is log base e of x. Now if we rearrange this equation, we get e to the power of y equals x. So if I go e to the power of both sides, e to the power of ln x, because e to the power of and ln are inverses, we end up with just x on the right hand side of that equation here. So here we've got an equation x equals e to the y. Now I'm going to do something tricky here. I'm going to do the derivative here with respect to the variable y. Okay, so I'm going to do dx dy is equal to, now if the derivative of e to the x is e to the x, when we're doing it with respect to x, the derivative of e to the y with respect to y is just e to the power of y. Right, so that's a little bit tricky there, but hopefully you'll follow me. If I had something like m equals e to the power of t, then dm dt would be e to the power of t, right? The derivative of this function m with respect to the variable t. So I've just done a very similar thing here, but with using x on the left hand side. So dx dy is e to the power of y. Now this next step is a little bit tricky, and the book has a little bit more detail, but I'm just going to ask you to believe me that these derivatives here behave like fractions. They're actually not fractions, they're limits of fractions, but they behave like fractions. We see that when we do the chain rule. So if I flip this upside down now, dy dx, I get 1 over e to the y. Okay, so again, I'll say these things aren't fractions, but they behave like fractions, which is cool. Okay, so dy dx was actually what we want to find. Remember, we started off with y equals ln x, and we want dy dx. We want what's the derivative of y with respect to x. We've discovered it's 1 over e to the y. And what is e to the y? If we go here, e to the y is just x. So there's our result. Dy dx is equal to 1 over x. That's it. So the derivative here of ln of x is equal to 1 over x. Now let's extend that result now and use some chain rule. What if we had y equals ln f of x? So it's a function of x now, not just x on its own. So it could be anything, x squared plus 2 or 3x minus 4, whatever it is. We've got this f of x function in here. Okay, so we could use the chain rule here to work out the derivative of this function. Just like we did before for trig functions or exponential functions, in all of these cases we need to multiply by the derivative of that inner function, in this case the f of x. So when we had sine f of x, the derivative was cos f of x times f dash x. Remember that result? When we had e to the power of f of x, the derivative was e to the power of f of x times f dash x. Okay, so in each case you need to multiply by the derivative of what I call that inner function, and that's going to be the same here for when we're dealing with the natural log function. The derivative of ln f of x is just going to be 1 over f of x, which is just like the rule says. Remember, the rule is just 1 over x, and then we multiply it by the derivative of f of x. So a lot of people just write that as f dash x divided by f of x. Okay, so that's how we've defined and can get those results, and you can see they're written out here for you, and I think that they're on the formula sheet also. So let's do some examples. So three quick examples here. For the first one, we've got 15x squared, and the derivative of log base ex is just 1 over x. For part B, 8 ln x, well that's just 8 times the derivative of ln x, so we know that's 1 over x, so it's just 8 over x. And for part C, ln 2x cubed plus 5x, here's where the chain rule comes in. So it's 1 over 2x cubed plus 5x times by the derivative of that of that function there, so 6x squared plus 5. So there is the derivatives of those three. This example, so log base e 2x minus 3, the derivative is just going to be the derivative of 2x minus 3 over 2x minus 3. Simple as that. Once you do a few of these, you'll get the hang of it really easily. Part B, ln x cubed plus 2, again, 3x squared over x cubed plus 2. So it's just derivative over the original function. Okay, part C. We could do the same thing in part C. We could say, what's the derivative of the top line there? And divide it by x plus 1, x minus 3. So if we expand this out, we get x squared minus 3x plus 1x is minus 2x minus 3. So the derivative of that is 2x minus 2. And that would be our answer, which is correct. But also there's a better way of doing part C, and I want to show you that because it will save you some time sometime. We know from the log rules that log AB is log A plus log B, correct? There we go. So I've just used some log rules to simplify that, and now when we do the derivative, so let's say if this is y equals that, I'm going to say y dash is equal to, now we can just do the derivative of each term. So the derivative of ln x plus 1 is just 1 over x plus 1. The derivative of ln x minus 3 is just 1 over x minus 3. Okay, and that is the exact same answer we got before. Let's just prove that that's true. So combine the fractions, x plus 1, x minus 3. X plus 1 goes into this x minus 3 times. So we get x minus 3 on the top there, plus x minus 3 goes into that x plus 1 times. So we end up with, on the top line, 2x minus 3 plus 1 is minus 2 over x plus 1, x minus 3. And you can see that is the exact same answer that we got before. I like the second way of doing it. A lot of the times these questions can be made a lot simpler if you use the log rules first to simplify before you do the derivative. So this one's a little bit different. You could expand out the brackets. Again, use your log rules. Y is equal to ln 2x minus 5 squared. Remember the 2 comes down the front there. So we've got 2 ln 2x minus 5. That makes life easier. The derivative now is, just think of that 2 out the front, and the derivative of ln 2x minus 5 is the derivative of 2x minus 5 over 2x minus 5. So we end up with 4 over 2x minus 5. Nice and easy. Now you could, if you wanted to, expand this out and do it the long way, but I think it's a lot easier to use that log law first, bring the 2 down the front, rather than expand out the bracket. So now that we know this rule, we can also do it with the chain. We've done the chain rule, so now we could also use the product rule or the quotient rule to use ln x in these kind of derivatives. So just look at part C here. We've got x cubed ln x. So we've got u dash v plus v dash u. I've just written it in a slightly different order that I would do. But u dash v plus v dash u. So u is equal to x cubed. V is equal to ln x. U dash 3x squared. V dash is 1 over x. Okay, so I've just put it in that formula. U dash v plus v dash u, which gives us that answer there, x squared plus 3x squared ln x. So you can see that we're using the product rule to get the answer here. Now I would also go one step and say that's x squared 1 plus 3 ln x, because again, when we want to solve that equal to 0 to find the stationary points of this function, it's much easier to solve it in this point here. I can see x equals 0 as a solution, and I can see 1 plus 3 ln x equals 0 as a solution. So we get ln x is equal to negative 1/3 e to the power of both sides. X is e to the negative 1/3. That's another stationary value or stationary point on this curve that you might be asked to find. And again, this might be in the non-calculator section, so they might ask you to find the exact x value of the stationary point, and there it is. It's e to the minus a third, or 1 over e to the third, or you could write that as 1 over the cube root of e. In part D here, we're using the quotient rule. So u is ln 5x, v is equal to x. U dash. So ln 5x, the derivative would be 1 over 5x times 5. So 5 over 5x, which is actually just 1 over x. And v dash here is equal to 1. So we put that in the formula. U dash v, so u dash v minus v dash u over v squared. And simplify it. So 1 minus ln 5x over x squared. So there we go, using the quotient rule now.